Let's pick up where we left off. So we're talking about refraction, and just as a reminder, if you've got two materials with a different index of refraction, that light will refract or bend as it goes across that interface. How much it bends depends on Snell's law. Whether it bends towards the normal line or away from the normal line depends on if you're going from high to low or low to high index of refraction, but again, this would tell you that too. The larger the difference between these two indices, the more this light's going to bend. Of course, in an extreme, if they're the exactly same index of refraction, it won't bend at all. And then the bigger the difference between these two, the more you'll get things to bend. We talked about index of refraction as a measure of how fast light appears to be going through the material compared to how fast it goes in a vacuum. And the reason those would be different is because our light has to work its way through a material through an absorption and readmission process. And that absorption readmission takes some time, and different materials have a different way of doing that, which gives you different index of refraction. We talked about a special case where if light is going from a higher index of refraction material trying to get out to a material that's got a lower index of refraction. So let's say this is 1.5 and this is 1. There's a special angle right here called the critical angle at which my refracted beam goes right along that interface, or another way to say that is my angle of refraction is 90 degrees. So when this angle of refraction is 90 degrees, we are at the critical angle. And so, just do this real quick, from Snell's law, we can figure out what critical angles are. Oops. Because this is going to be 90 degrees at that critical angle. And this depends on what your other material is. If it's a standard problem where you've got a piece of glass and it's surrounded by air, then this is a 1, but it could be surrounded by something else. Maybe it's a piece of glass and water. That would give you a different critical angle. For this particular case, if you're surrounded by air, that's how you get the critical angle. So we talked about that a little bit. Today, I want to take a look at something a little bit different. Not different, I should say, but kind of an extension of this. Is what happens if I don't have monochromatic light. But I've got light with different wavelengths in it. So let's say I've got light that's got these two colors in it. What happens when that goes through that interface? Yeah, that light's going to bend. And if I'm going from a low to high index of refraction material, which way is it going to bend? So here would have been straight. Is that going to bend towards the normal or away from the normal? It's going to bend towards the normal. Now the question is are the red and blue going to do the same thing or something different? So what's the difference between red and blue? Both are electromagnetic radiation, right? So yeah, really the only difference is in the wavelength. Red is longer wavelength, blue is shorter wavelength. And then what corresponds with that is the amount of energy they carry. That's different. If they have a different wavelength, they carry a different energy. So who carries the more energy? The longer wavelength red or the shorter wavelength blue? Short wavelength blue. Well, wait a minute. That means if we send that light into some material, that light, the electric field component, is getting absorbed and re-emitted, so the light's getting absorbed and re-emitted by the molecules in there. They carry different energies. There's going to be a different interaction as they go through that material. What that's implying then, since that's how we came up with, oops, I erased already, how we came up with index of refraction, that means these two, when they come into this material, it's almost like they see a slightly different index of refraction from each other. Yeah, we say, oh, the glass has an index of refraction of 1.5. As these guys come in, it's almost like they see it slightly differently. Next question then would be, who sees the slightly larger index of refraction? The higher energy blue or the lower energy red? I guess a way to kind of figure it out is who's interacting more with the material. Another one's 50 degrees each other. The higher energy wavelength is going to get those little molecules to oscillate a lot more. So I guess this is maybe a bad analogy, think of it this way. If I have to oscillate this much or this much, who's taking more time? Hopefully. This is a bad analogy, but a way to kind of think about it. So the higher energy is causing more interaction. That's going to take more time, as if it's a little bit slower through the material, which means a slightly larger index of refraction. So what's the consequence of that once these two beams hit that interface? Yep. Again, you get more bending the larger the difference between these indices of refraction across that interface. So if blue's seeing a little bit larger index of refraction, you'll actually start to get these guys to split. So you should bend those a little bit more. So not straight, but it's bending. And what you're getting, how many of you have taken word origins? Nobody?
I've taken what, sorry?
Word origins.
Word origins.
Yeah.
Medical terminology.
Yeah. Oh, yeah. Maybe they call it medical terminology now. This is a good one for that class. Because what's chromatic mean? It's a fancy word for what? Color. What's dispersion mean? That's exactly what this is. It's color spreading. So what you're seeing is chromatic dispersion, color spread apart. And let me show you a quick example of that you probably have all seen, but I'll go ahead and set this up. And actually, let me turn some lights off. So I've got a magic pyramid, and if I shine this white light through the magic pyramid just right, you'll see down here that white light getting spread. So what it's doing, I'm going to turn it sideways for a second. I'm going to send the white light in like this, and it's going to come out like that. So when I turn this way, the light's coming in, I don't know how well you can see it. It's coming in here and out here, so I can get it bent down here where it's dark so we can actually see it. And you can then see the colors that are in that light, and you'll see the red gets bent the least, the Blue gets bent the most, and you get the whole Roy G. Biv in between there. So again, what's happening is each of the colors that's in this light sees a slightly different index of refraction in this piece of glass, so they bend differently. But again, the red bending the least and the blues bending the most. You guys have all seen that before, right?
And that's where you get the cover of, what was it, Dark Side of the Moon?
Yep. And they did have it right. So with that, let's take a look at rainbows and what causes those. Let's see, let's try this on you guys. If you see a rainbow over here, you know where the sun is? It'd be over there. Okay? So let's take a look at this. So, say here's the sun way over here, and here's a raindrop. Make a big one so we can see this. So what happens is, the light comes in. Let's try this. Try some colors here. So here comes a ray of light from the sun, and it hits an interface between two materials. We've got air out here, we've got water right there. Water has an index of refraction of 1.33. So yes, that light's going to bend, and if that light has different colors in it, you're also going to start to get chromatic dispersion. And the blue bends more than the red. So what comes to at this point, here's your red, and here's your blue. Hits the backside of that raindrop. And what happens, and this sometimes gets ignored, anytime light hits an interface, it's always going to reflect. So you're also going to get a reflection like this. Usually you're just talking about the refraction part, but you're going to get a reflection. So you can get a reflection off the back of that raindrop, and it's going to follow the law of reflection. So the angle going in is the same as the angle going out. And what happens there is, because of these angles, after the reflection, these two beams cross. Get that a little bit better. Then the light hits another interface, so the light's going to bend some more. But notice what we've got is chromatic dispersion. And I should have mentioned this the other day. You know, we talked about that Roy G. Biv, and you guys learn like blue, indigo, violet. A lot of times what you'll hear scientists talk about is one side is the red side, the other side is the blue side. So a lot of times red and blue are used for distinguishing long wavelength versus short wavelength. So there's what comes out of the raindrop. And we've got that chromatic dispersion. The whole Roy G. Biv is in between these. So what color is at the top of a rainbow? What color is at the top? Let me look at rainbow. Fine, you've seen rainbows all your life, right? What color is at the top of a rainbow? Oh, come on.
It's actually the blue side. It's just usually it's too faint for people to see it. Unless you get.
You guys really don't know? After seeing them all your life? Oh, we better have somebody check. it up. You sure? It's on the internet, so it must be right. What's it look like? Of course it's red on the top. Well, wait a minute. It says red, doesn't it? Shows a nice picture of it, doesn't it? Looks like the rainbow you've always seen. So how come that says red's at the top of the rainbow, but I just do it this way? They're both correct. Just think about this. What's that? Let's see how you're actually going to see this thing. So we draw over here. Here's a drop. Here's a drop. Here's what comes out of these drops. Angle this a little more. There's the blue. Here comes the red. Okay. But you are right here, looking at these raindrops. What color is this drop to you? What color is this drop to you? Sure, this one looks red. This one looks blue. Where did the red go here? It's over here someplace. Where did the blue go here? It's over here somewhere. But think about this. What does that imply? If you move. Let's say you move up to here. Let's say you move to here. Now what color is that drop? Now that one looks blue. What color is that drop? That one looks red. In fact, what did you just see that rainbow do as you moved? It moved. Which is why, even though I tried when I was like this, you can't find that darn pot of gold. How many of you actually did try that when you were little? Come on. You tried it once. You saw the rainbow, it's like, I swear I see where it's hitting. I'm going to go over there. How many tried it? Anyone succeed?
Yeah.
That's what's happening, is as you move, that image that you're seeing is moving with you. These little drops will change color. So that's how you end up with a red at the top of the rainbow, blue at the bottom, yet the whole void you did in between. Have you seen double rainbows before?
I was about to ask about it. What about the double rainbows?
Do you know what the order of the colors is in a double rainbow? Take a look. The second one is inverted. It'll be backwards of this. So let's see if it's true.
Yeah.
It's inverted, isn't it?
I figured that was like, I figured that was going to explain why the double rainbow was.
The double rainbow comes off a second reflection here. And when you get a second reflection, these things flip over or flip back again. And so coming out of the drop, red is on the top, blue is on the bottom, so it'll give you an inverted rainbow. So whenever you see that double rainbow, that's coming off a second reflection, that second rainbow. Which then gets us back, any other questions here? Does that make sense of how you end up seeing a rainbow that you do? That gets us back to that little symbol we saw on the license plates the other day. Those little symbols in here. So notice that with this picture, this is an index of refraction of 1.33. What would happen if, let's ignore the chromatic dispersion part, what would happen to that ray? And notice, again, without the chromatic dispersion, I came in like this, I came out like that. What's going to happen to this angle if I increase that index of refraction? Say I start, somehow with the magic dial, I start turning this up. What's going to happen to the angle of this thing that popped out? I can start to get it to bend more and more and more. Eventually, if I get this just right, if I get the index of refraction just right, I can get that ray that's coming back out to go right along the same direction as the ray coming in. Hey, we saw that before in a whole different application. You know what we just made again? Which really isn't getting closer to that disco ball. There's a retroreflector made out of little glass beads. In fact, a lot of the reflectors you see out on the highways are this kind. We saw that other kind with the little corner cubes. But if you take a look at road signs, they put this now on paint that they use in the stripes in the road. They put little beads that are designed to be little retroreflectors. So that whatever light hits it, it's going to get reflected back to the source. So you and your headlights see, oh, the sign lit up even though there's no lights on it other than your headlights. So it's basically made out of little, or it's embedded with little beads that are retroreflectors like that. Those are also in here. These have little beads in them that are little retroreflectors. What they did that's really sneaky about the little symbols you saw here that you could only see at one angle is roughly the way they do this. Again, it is proprietary, so they don't tell you exactly how, but it's roughly like this. Is when they make this, they put a coating that's photosensitive on the backside here of this bead. And they'll take a little symbol, shine a light at a specific angle that casts a shadow on those beads. That I think what they're doing is they're burning off this coating everywhere that shadow doesn't cast. So what they're doing is, if this is the angle they sent the light in as they're trying to embed that in there, it would say hit here and come out like that. Then they let light hit all the rest of this, burns all that off, and they leave one little spot here that's not reflective. So this little spot's not reflective. So notice light at any other angle pops back out, no problem. But if I look at one specific angle, right like this, and my light hits that, it doesn't reflect back out, and you see that bead a little darker than the surrounding area. Look at any other angle, and whoop, all of a sudden that little dark spot, that was a bad picture, my little dark spot disappears. That's roughly how they actually do that with those little beads. Again, it's a little proprietary how they actually do it, but it's the basic idea. Any questions to hear? What this sets us up to start to do then is, now that we know a little bit about reflection and refraction, is we can start to make useful devices out of these. We already saw some quick examples, like making those little pieces of glass like this that can reflect light a certain way, taking advantage of the critical angle. Let's take a look at mirrors for a bit, and what you can do with specifically spherical mirrors. So mirrors that, if we continued them around, would go around in a sphere. So here's an example of a spherical mirror. So this side's kind of shiny, this part's curvy. And if I continue this all the way around, it would make one great big old sphere. We just took like a little piece off that sphere to make this piece right here. So with spherical mirrors, a few things here. So here's, say, the mirrored part itself. And again, if I continued it, of course, on the plane of the board, it would look like a circle. In real life, it would be a sphere. Notice there's a center of curvature. So right in the center of what would have been that sphere. And halfway out from the surface to that center of curvature, there's something else here that's interesting. And to get an idea of what that is, let's take a look at an example. Let's say I've got a mirror shaped like that, and I'm going to draw something here called the optic axis. It's just a reference line. I can continue with that if I want. And what we're going to do is send in light rays that are parallel to that optic axis and see what happens. So switch colors here. So let's say I send a light ray like this, and it hits the mirror right there. Well, it's going to reflect, and it's going to follow the law of reflection, so whatever the angle going in is the same as the angle coming out, as measured from the normal line, or the line that's perpendicular to the surface at that point. So here's my normal line. So here's the angle coming in, angle coming out is the same, and I'll get a reflected ray like that. What happens if I send another one this way? So parallel to that first one, and it hits right there. So same thing, follows the law of reflection. In this case, it'll reflect about like that. In fact, if I take any ray parallel to those, something interesting is going to happen. So here comes another one, reflects like that. Here comes another one, reflects like that. And notice I've got something happening right there. All my parallel rays end up reflecting through the same point. You know what that point's called? So what did we just do to all those parallel rays? We focused them down to that single point. That marks the focal point of that particular mirror, and that focal point sits halfway between the mirror and that center of curvature. By the way, what happens if I've got a mirror like this, shaped that way? There's that optic axis, and I send a ray of light in like this, and it hits right there. Which way is that one going? It follows the law of reflection. Here's the line that's normal to that surface, perpendicular to that surface at that point. So this one's going to go like that. If I send one like this, it's going to go about like that. So does that kind of a mirror have a focal point? Let me back up. Does that kind of a mirror have a center of curvature? Sure it does, because I can extend that around like that, and there's the center of curvature. I will contend it does have a focal point, and it's exactly like the other one. It's halfway to that center of curvature. Because notice, my picture didn't work quite right. Let me fix it. that if I extrapolate my reflected rays, well, still missed a little. Notice they still will go towards a focal point. It's just the focal point's on the back side of the mirror. Notice we've got two different kinds of mirrors. We've got one that does this. What did this do to those reflected rays? Brought them all together. In other words, those reflected rays converged. So this is a converging mirror. What did the reflected rays do there? They didn't converge. From your medical terminology class, it's the opposite of converge. They diverged. They went apart. This is a diverging mirror. And knowing that stuff, we can start to then get an idea of what kind of images these two types of mirrors will produce. And we're going to do that a couple different ways. One, sort of a graphic way of doing it, and another a mathematical way to do it. But we'll have two different ways. Given a mirror, whether it's converging or diverging, knowing a little bit about that mirror, where the focal points are, we can figure out what an image is going to look like based on where we stick an object in front of it. But let's take a break before we get to that. It's probably a good time to stop for just a few minutes. When we come back from the break, we'll take a look at how to figure out images both graphically and mathematically. So let's go ahead and start up, and let's take a look at how you could figure out what images are going to look like by sketching things out. What we're going to be doing is looking at what are called ray diagrams. And I've noticed that a lot of standardized tests that people take for professional schools, for some reason, like ray diagrams. So I'll make sure anybody that has to take like an MCAT or a dental thing or whatever else you guys take, that you know how to do these just in case they show up. I don't know why they like these, but they seem to show up on these tests. So let's start with this kind of a mirror. And we'll draw an optic axis. And a couple other things you'll see on here are a focal point and a center of curvature. Here's a center of curvature, here's a focal point. And let's stick an object somewhere. And what I'm going to do is make a little candle. I'll stick it here. A little flame on the top. So we'll use that as our object. And what we're going to try and do is figure out, if I stick that object there, what's my image going to look like and where is my image? And we're going to do it figuring out some rays, and what we're going to do is this little trick. As mentioned before, I know there's light being reflected all different directions off of the tip of this little marker, because all of us can see it, so there's light being reflected all different directions. So a whole bunch of different rays that we could pick from. Or to draw it here, there are a whole bunch of little rays coming off of the tip of this little flame right there. What we're going to do is select 3 special rays. And the reason we're going to select these 3 is we know exactly what these 3 are going to do when they hit that mirror. And this is hard to put into words, so we're going to have to actually try it to see what these really mean. But you're watching for 3 different rays. So again, I'm going to sort of put it into words, but it's hard to put into good words that work for everyone. You'll see what I mean here when we start to do some other examples. This is parallel. If I take a ray that's parallel to that optic axis, and it hits that mirror, we know exactly where that's going to reflect. Which way does that one reflect? Right through the focal point. But I'm going to be a little more careful on these. I'm going to draw these guys a little bit lighter, because what we're really going to be interested in is the reflected rays. That one's going to go right through the focal point. Our second special one, next goes through focal point. if I send a ray through the focal point. So I'm going to come off the tip of this. Of all these I could possibly choose, I'm going to choose this one. Any idea where that one goes? If a ray parallel goes through the focal point, a ray through the focal point reflects parallel. So that'll go this way. And then we have the easy one. A ray right through the center curvature. I'm going to have to extend my mirror here. Where does it go? It's through the center of curvature of the sphere. Notice that it's right along the normal line to that surface right there. Goes right back on itself, right back through that center of curvature. Oh, notice what happened to my reflected rays? And this is where it helps to like make your reflected rays prominent, because otherwise you start to get a lot of lines. Here's a reflected one. Here's a reflected ray. Here's a reflected ray. Notice anything special? They all crossed somewhere. That locates the image of whatever object you used to draw those lines. What did we use? The tip of that flame. So the image of the tip of this flame is right there. See if this makes sense. If I did all the same thing with the bottom of this candle, a ray parallel would go through the focal point. A ray through the focal point goes parallel, ray through the center curvature goes through the center curvature. Whereas the image of the bottom part, it's right along this optic axis. I could do it for the middle of the candle, the top of the candle. The easiest way to do it, as long as your object's sitting on this optic axis, which they all are going to be, all you have to do is figure out where the top is. Here's the top of that flame. Everything else is like that. So I ended up with an image that was upside down and a little smaller than what my object was. So the best way to do this is to actually try it and see what the nuances are of figuring out what these three rays really are. So I put together some little practice pages, and if you botch one up, I've got some extras here, and I'll post these on D2L so you can practice some more. Let's see if you can sketch these. And I'll give you some rulers to help with your straight lines. Let's see if you can figure out what the images are going to look like for these three cases. So we gave you some rulers so you can make nice straight lines. And again, to figure out ultimately where that image is going to be, you want to pay attention to the reflected rays. And remember, these are mirrors, so your rays are reflecting off of them, they're not passing through them. So let's see if you can figure out what these are. And again, there are some nuances to these three rays, but it is these three that we're going to be looking for. Where the reflected rays cross will identify what, or it's going to help us identify what that image is going to look like. Let's see what you guys come up with on this. first one's pretty straightforward. It's the next two that get a little bit more interesting, so let me see what you come up with on. And again, what you can use is the very tip of that little flame is the spot you would mark. And once you figure out where the image of the tip of the flame is, draw your little candle to show the whole image. So again, the next two are a little bit trickier. So on this one, make sure you continue with it. Okay. You're jumping to the next one. And again, remember, these are mirrors, so the light rays reflect off of them. Let's see what you come up with. You think you have something on the second one? Let me know, or if you're stumped on the second one, let me know.
I'm ready.
It's gonna reflect off that
So
here.
you need, with this one go away.
So again, your rays are gonna reflect off the mirror. You need to know, do I have a converging or diverging mirror? And you're gonna pick 3 rays. Because there's 3 rays coming off the tip of that little flame. If you pick the right ones, you know what they do when they hit that mirror. Yep.
Are those the 3 right ones?
As you're finishing up, I'll show you another way to do this. And that's with a couple simple equations where we can actually calculate an image. So let me show you this real quick. And it's these 2 equations. That 1 over the focal length of that mirror is 1 over distance to the image plus 1 over distance to the object. Let me switch those. Object and image. Same thing. And the magnification of that image is the negative of distance over image, distance over object. Only thing to watch with these, they're pretty simple to work with. In fact, you've dealt with this kind of an equation. We did things with resistors and capacitors, so you hopefully you get about using those. We have some sign conventions to take care of here, though. Of what pluses and minuses mean for all of these. For distance to the object, let me just write these all real quick. If it's positive, that means it's in front of the mirror. Negative means behind. For distance to the image, if it's positive, that means it's a real image. If it's negative, that means it's a virtual image. What those mean, and you'll see that with your ray diagrams, if the actual reflected rays touch the image, that's a real image. If the actual reflected rays don't touch the image, that's where you had to do the extrapolation behind the mirror kind of thing, that's called a virtual image. The positive and negative on our numbers are going to tell us whether it was real or virtual. For the focal length, the plus and minus tell you whether it's a converging or diverging mirror. And the magnification, the plus and minus tell you whether that image is going to be upright or upside down or inverted. One of those things I wrote up there should not make sense right now. I'll show you how it's going to make sense, but it shouldn't make sense right now. Any of those seem odd? That doesn't seem odd? That your object's behind the mirror? Here's how that's going to happen. It won't happen with an object in a single mirror. Where that will happen is later, if you've got more than one optical element in your system. Let's say we've got a lens and a mirror. What could happen is a case like this. Say here's your object, and maybe I've got a lens and a mirror, and I want to know what kind of image is going to be formed by that. What we're going to see later is the way you solve this kind of a problem is you do what we're about to do one by one, where the image of the first one acts as the object for the second one. So you could have a case like this where this particular lens forms an image over here. That's going to act as the object for this one. And notice it's on the wrong side. But mathematically, we have a way to handle that. But with just a single mirror, you have to have your object here in front of the mirror. So you're not going to get a negative distance to the object unless you've got multiple elements that are casting something to the other side. So we'll see that later. But for now, let's take a look at an example and see how this would work. Let's try this one and see if it's consistent with what you found with your ray diagram. So let's say we've got this case. I've got a converging mirror with a focal length of 10 centimeters. And let's put an object out here. Let's make it 40 centimeters from the mirror. And with that, let's see, can we describe the image formed by that mirror by doing some calculations? So first, let's figure out where that image is going to be. So this equation right here can tell us where that image is going to be. So let's solve that for 1 over distance to the image. That's just 1 over the focal length minus 1 over distance to the object, which is 1 over, well, I see a 10 centimeters there. Is it a plus or minus 10 centimeters? And I would recommend putting the sign in there just to make sure that you've accounted for it. So all we need to know is that a converging or diverging mirror? That's a converging mirror, so that is plus. So that's plus 10 centimeters. minus 1 over distance to the object. I'm 40 centimeters away. Am I in front of the mirror or behind it? I'm in front, so that's plus. And as we saw when you're dealing with capacitor equations and resistor equations, notice that whatever I get here is not my answer. I have to take the inverse of that. So this itself is 3/40. So my image itself is over here at plus 40/3 or plus, we'll do that on a calculator instead, 13.3 centimeters. Oops, so there's one piece of information that's going to help me figure out what the image looks like. My magnification is minus from the equation. Now I need to add in my distance to the image, distance to the object. So distance to the image, there it is right there, plus 13.3 centimeters. Over distance to the object, that was a plus 40 centimeters, which gives me a minus 0.33. So there's my numbers. Let's see what that all means. So, where is my image? What's the 13.3 centimeters tell me? That's distance from the mirror. What does the plus tell me? That tells me which side of the mirror. Is that right or left? That tells me reflected rays actually touched it. Where are the reflected rays? To the right or the left? I'm going to hit that and go that way. So that says 13.3 centimeters on this side from the mirror. Is it going to be bigger or smaller than the object? What this is it's almost like there's little times there. It's 1/3 times the size of my object. So it's smaller. Right side up or upside down? Upside down. That's your first one on your sheet with your ray diagrams. Converging mirror, object outside focal point. The advantage of this is now we know exactly where things are. It's exactly this far from the mirror. We even found out, yeah, it's on the left side, exactly how much smaller it was, and yeah, it's upside down. So that's how you calculate these. Any questions there? The reason I did it this way, rather than say in front or behind, is that way we're going to use the exact same conventions when we deal with lenses. The difference with lenses is light goes through them. So we're looking at refracted rays, they're going to be on the other side of a lens. In fact, speaking of lenses, we can figure out where images are going to be and what they look like the same ways. We can use some ray diagrams. So here's some examples of those to play with. And we can calculate it. Here's the ray diagram here. And it's going to be pretty similar to what we've been doing with the mirrors. The only thing to recognize is that these are lenses, so the light rays are going to go through them. So let's take a look at this example, and then I'll have you guys try it. So we're specifically using spherical lenses, and what that means is if I continue each side around, this would form a sphere, and this would form a sphere. So each side has a curvature that would make a little sphere. In fact, let's take a closer look at what's really happening with this shape when I send light through that. So let's put an optic axis through here. If I send light into this thing with that shape, notice I hit an interface here between two materials, in this case, say air and glass. Maybe we made a lens out of glass. That means it's going to bend. Here's the normal line to that interface. Here would be straight through. If I go from low to high index of refraction, I'm bending towards or away from that normal line. From low to high. Towards. Here's straight through, there's towards it. So I bend this way a little bit. I get another interface. Here's the normal line. Here would have been straight through. Now I'm going from high to low index of refraction. Which way are we bending? Away from the normal line, but that's down again because of the shape of that side. So altogether, I made that particular ray go like this. And here's my refracted ray. If I take another one here, does the same thing like this. And if I take other rays that are parallel, notice we're going to get a spot right here where they cross. So I get a focal point. A difference between lenses and mirrors is I also have a focal point over on the other side. They could be different if these curvatures are different, but for us, we're just going to have the same curvature on each side. So whatever the focal length is on one side, I'm going to have another one over on this side. So one difference is we have two focal points. What if I've got a lens like this that's shaped this way? And I send light in. Notice at this point, here's the direction of my normal line. Here would have been straight through. I'm going from low to high index of refraction, so I'm going to bend towards the normal line. But in this case, because of the way that surface is shaped, that's up. I get this interface. Here's the normal line. Here's would have been straight through. I'm going from high to low index of refraction. That bends away from the normal line, but that's also up. Send one down here, same kind of thing happening. And like you saw with your mirrors, my refracted rays are diverging, but there is a spot back here if I extrapolate them, then they'll cross. And again, I can define a focal point here and a focal point over here. And again, they could be different if these curvatures are different, but we'll just deal with lenses that have the same curvature on both sides, so the focal lengths will be the same. Notice that we've got some a little bit more complicated things going on because there's two different surfaces where I'm getting the refraction. I can have a converging lens that's shaped like this. I can have a diverging lens like this one. To simplify this, what we're going to do in our little sketches, even though this isn't the real case of what's really happening, what we can do to simplify this is draw a line right through the center of that lens and assume all of the refraction happens at one time right in the center. Even though in reality it happens in both surfaces, we can actually draw a picture like this, where here's a ray coming in, we'll run it all the way to the center and then do just one bend. Run it all the way to the center, do just one bend. That'll simplify our pictures a little bit. If it's a diverging lens, we can do the same kind of thing. Go right down the center, run your ray all the way to the center, and then diverge. All the way to the center, diverge. That just simplifies our drawing rather than have to worry about two different surfaces. What about this case? What if I have a lens like this? Is that a converging or diverging lens? So that's converging, that's diverging, that's easy. Want the hard way or easy way? Oh, it's late Friday, you want the hard way.
Yeah.
Notice, this is a divergent side. This is a convergent side. So the real question is who wins? What you can look at is, let's look at those curvatures. And which one has the tighter curvature? The converging or diverging side. Notice the converging side has a tighter curvature. That means that side is stronger. So the converging side would overpower the diverging side to give you an overall converging lens. That's the hard way. Want the easy way? If it's fatter in the middle, it's converging. If it's fatter on the ends, it's diverging. So you guys tell me what this is. Fatter in the middle, it's converging. Fatter on the ends, it's diverging. Don't make this right. And as that's going around, tell me what this one is. Yeah, fatter in the middle for sure. That one's converging. How about these ones I'm passing around? Where is it fatter? I'm going to pass yours over here. All I have to do is feel it. You can tell. So, what I passed you guys with the results of that. Okay, on ray diagrams, same kind of thing. We're looking for 3 different rays. Of all the possible ones we can choose, there's 3 that are going to, that we know exactly what they do when they hit that lens. And here, I would recommend doing them in this order, because the only complicating part here is there's 2 focal points. So do this one first. So where do you suppose this one goes? And 2 things to remember. Is it a converging or diverging lens? And it's a lens, so those rays are going through now. So which focal point am I going to use? Left or right? So it's a converging lens, so I know it better bend down. How much is it bending down? If I went in parallel, it's going to go through this focal point. I can only use a focal point once. That's the reason for doing this one, is that it ties up one of your focal points. Then the next one, you're going to use the other focal point now as your guide. And just like we saw before, that one goes parallel. And then just like the mirrors, we've got an easy one. Just write it this way, it keeps going. If I send a ray right through the center of that lens, it's not going to refract at all. It'll just keep going in a straight line. And just like we saw before, now I want my refracted rays, they're the ones on that side, I see where they cross, and that then shows me what my image is gonna look like, just like we did with the mirrors. So try that with those 3 lenses and see what happens. See if we can get those to work. So you can figure out these 3 ray diagrams for lenses. So again, remember the rays go through the lens. We're looking for refracted rays. You can only use a focal point once, but your 2 focal points are going to be your guides for your first and second rays.
So, how do you do the third ray?
Send it right straight through the middle of the lens.
And it just goes straight, it doesn't go straight on. So it's literally a straight line.
Yep. Yep. So that's nice easy. So again, once you've tied up one focal point with that first ray, then figure out how you're going to use that second focal point to guide you for that next ray. So when you get done with these, that's it for today. Just